So we had the notion of the derivative of a function of a single variable. Okay, and the definition of that is here in equation 1.1. So we have this notation f prime a or that, except you'd read that as the derivative of f at a, the derivative of f evaluated at a. And this was defined with this definition here. It was the limit as x tends to a of f of x minus f of a over x minus a. To say quickly in one go, so to speak. But how did we think about this? Well, this fraction here, f of x minus f of a over x minus a, this was a ratio that was measuring the change in behavior of the function, value or behavior it has at f of a, comparing it to its values at nearby points. Okay, so we thought of x as being a nearby point to a. And if you look at the numerator, what you're looking at there is just simply the difference in the two values. Okay, by how much has the function changed value when you evaluate it at x compared with at a? F of x minus f of a. Value of this difference is going to be small, or if the function makes a large change in behavior, if the difference between f of x and f of a is large, then this difference will be large. But it's not so much, I mean, depending on how far away you move from a, you might encounter different changes in value of f. That's not really so important. Really, we should also take into account by how much we've moved away from a. Because even a very slowly changing function, if you move far enough away from your base point a, you may observe a large change in value. Okay? But perhaps you should also take into account by how much you've moved away from a. So that's why we look at the change in value of the function here in the numerator relative to the change in value that we've made in the argument. Okay? So you look at the difference between f of x and f of a relative to, so in other words, as a fraction of the difference between x and a, the distance between the 2 points where you've evaluated it at. So that gave you this number, this quantity, which was the derivative of f evaluated at a. In alternative notation, we have this other type of notation, df dx, the derivative of f at x. It's still the same thing. We're still doing it at a base point a. This limit written as, not with x minus a here, but here you're using a as the base point. And rather than using a separate point x, which you're letting approach a, you're using h as some kind of offset variable. So the new point is the old point a plus an offset. And then the distance, what was the distance between x and a, is now just the size of the offset. That's going to be the distance between the base point a and the nearby point a plus h. Okay. So in either case, I mean, they're both the same thing, just expressed slightly differently. We've got this relative change in value, but we're looking at its limiting behavior. Okay? As you let the nearby point x converge to the base point a. And what's going to happen then is this relative change quantity. So you can evaluate this relative change quantity at a nearby point x to a, and you'll find various relative changes. But when you take the limit of it as x approaches a, what you end up with is this number called the derivative of f at a, which captures the kind of instantaneous rate of change of x at that base point. And indeed, we had a familiar picture which we associated with this, okay, which we should also cast our eyes at again, have a look at again. And just compare it what we're going to look at shortly. So this is a review of the one variable case. What was the graphical interpretation or the graphical meaning? The graphical interpretation of the derivative of the function f at a. You'll be familiar with this kind of sketch from last year. So we have some function f. We've got the x-axis here, the f of x-axis here. We've got some base point, might be this one here, a. And this here would be the value of that the function takes at a, approximately. Height of the graph, above the point A. And what we have then associated to that is this tangent line. Okay. This is the tangent line to f, or to the graph of f at A, or at x equals A. And f prime A is the slope, or sometimes called gradient, of the tangent line. You might also in this picture think of a nearby point, say A plus H. I'm using this offset H notation here. If you look at a point offset from the base point, like A plus H, the graph will have a certain height there above that point. And this line, okay, so the black dotted line is not the tangent line. You can call that like a chord through the graph of f, if you like. The quantity f of A plus H minus f of A all over H. This is the gradient or the slope of that black dotted line. The slope of this line here. And so as you take the limit as H approaches 0, this nearby point A plus H, of course, is going to converge to the base point A. And this chord through the graph, the straight line joining the 2 points on the graph at A and A plus H, well, as H goes to 0, this point is going to travel along the graph, so to speak, until it converges to the point A. And at that point, this chord will have converged to or arrived at the tangent line, if you like. Okay. So that's kind of a quick look at the definition of the derivative that we met last year, and linking it to the graphical interpretation of the function through its graph. Any questions you want to fire at me now based on that? Or in general, don't be afraid to ask for clarification during the lecture. I welcome such things. And if you're sitting there with a question humming away in your mind, it's more than likely the case that several other people are thinking that same question as well. So please don't be shy or afraid of calling out questions. Okay. So let's look now at the situation of two variables. Okay, so we'll switch back to that position in my notes. As usual, I'll put scans of all these handwritten pages up as a comment on the lecture recordings, as usual. So I'm recording away. Okay, so how do things look when we look at functions of more than one variable? Now we're going to say a little bit here about what we mean by, functions of two variables and so on. But we're just going to dive in and start to look at the definition of the partial derivative. Okay? This time we're going to be looking at a function, not of one variable, but a function of two variables. Okay? So f now, in the one variable case, you've got the situation f of x. So you supply an input x to the function, and it returns a value f of x. Okay? But here, we're going to start off, we'll generalize to more than two variables soon, but initially we're just going to look at the case of functions of two variables. Okay? So here our f requires two independent inputs, an x value and a y value, a first argument and a second argument, and then the function gives you back a real value from that. Okay? And what we attempt to do here is to imitate or copy the definition of the one variable derivative and adapt it to the two variable case. But there's two variables around, okay? So what we find is that we get two derivatives that we're going to differentiate with respect to one of the variables only, okay, at a time. So for instance, and these things, because you're only differentiating with respect to one of the variables at a time, these are called partial derivatives. So first here in 1.3 at the bottom of page 1, we're looking at the partial derivative of the function f with respect to the variable x. And well, it's traditional to use sometimes some of this other notation. So here, this is delta x, this quantity here. It's not a multiplication of two things of a delta and an x. It's not that. It's just a single quantity with a two-letter name. Okay? So most of us have more than two letters in our names, so mathematical numbers can have more than two letters in their names. That's just a single quantity, delta x. Yeah. So it's playing the role of h. You look at the f of a plus h up there, that one variable definition, this delta x is playing the role of that h. Just helpful to include the letter x in the name so we know which variable we're talking about. Again, we're going to look at the relative difference of the function f, okay, and take its limit. Okay? But the relative difference we're looking at the function f evaluated at some base point, xy, say, and we're evaluating f at a nearby point, but we're only varying one of the variables. Okay? If your base point is xy, a general nearby point close to xy in the domain of the function would be x changed a little bit and y changed a little bit. Yeah? That would be a nearby point to xy. Okay, but here we're only going to move to a nearby point, but we're going to keep the y coordinate fixed and just vary the x coordinate, or the first argument to the function. So the first argument to the function in this first term here in the numerator is now f of x plus delta x plus a little bit. Okay. The second argument, y, is still the same argument as is in the second term here. Okay. And we look at the difference between these two quantities, and this measures the change in behavior of the function f at those 2 points, the change in value of the function at those 2 points. And again, but that kind of only makes sense when you compare it to how far away you've moved. So we make it relative to the change in value of the coordinate of the first argument that we've introduced. Okay? So this ratio here, this fraction, is the relative change in value of f between the base point xy and the nearby point, still with the same y coordinate, but the x coordinate, x plus a bit, that bit being delta x. But again, to get the derivative, to get the behavior, the kind of instantaneous or quintessential behavior of the function f at the base point xy, we take the limit of this relative change as the change in the x coordinate that we're referring to here approaches 0. If you've got a good definition of the function f in kind of terms you can calculate with, be it some kind of polynomial function or some kind of standard function, you would hope to be able to express this relative change here and to maybe in some cases to actually just using pen and paper to be able to evaluate the derivative. We'll see in a moment an example or two like that. So that's the partial derivative of the function with respect to x. Equally well, we can talk about the other partial derivative of f with respect to y. Okay. Here, f has a first argument and a second argument, an x argument and a y argument. Okay? There's no reason why one is preferred over the other. Okay? So just as we had a partial derivative with respect to x, we can have a partial derivative with respect to y. And the definition is the obvious one. Okay, where now the change is just happening in the second argument to the function, in the y variable, so to speak. Okay, so we're comparing the value of f at the base point xy with its value at the nearby point xy plus delta y, relative to the change in variable that you've introduced, which is the delta y, and taking the limit of that quantity as delta y approaches 0. Okay, and this is called the partial derivative with respect to the y. Notice that, I'll do an example shortly. Notice that in contrast with the one variable case, in the single variable case, we It's traditional to use Roman letters for the d's, the differential operator, df, dx. When you're talking about partial derivatives, it's customary, traditional to use this curvy d. I think it's intended to be a version of the Greek letter delta. It's not exactly that. This is the correct Greek letter delta, lowercase d, but this is something like a corruption of that or a modified version of that. Okay. I've noticed some students are reluctant to change and they kind of want to keep using Roman letters d, but it's kind of, it looks odd. It's a bit rude, you know. Just as we have social conventions, you know, saying hello and so on, introducing yourself. You know, if you use Roman letters in your Ds, it's normally the case that you're talking about single variables to indicate to the reader and to yourself when you're reading back your own work. This alternative form of the D indicates that the function you're working with has got more than one variable. Okay, and it's traditional to use those. Okay. And some traditions are vitally important, such as we drive on the left, yeah, not the right. It's a meaningless tradition. It doesn't have to be that way, but it's pretty important that everybody sticks to it. Yeah. Now, not that this is so strong a tradition, but it's good practice, and people will question your mathematical credentials if you're using the wrong symbol. Okay. So let's just jump in and see one of these working in practice. Now, I've got most of the details written out in the notes itself, but I don't think there's any harm to just step through it again ourselves on the page, just so we don't go too fast and just so we can talk about and digest the details as we go. What am I doing? Document camera again. So this is example 1.1. So before we go any further into any further discussions, I just want to meet an example of these things. So we're going to consider the function f of xy. So we've got a two-variable function. It's not too complicated. It's a simple polynomial type function, quantity x squared multiplied by y. And it might have various partial derivatives. Okay, so what we attempt here is to obtain the partial derivatives of this function. Okay, so using the definition, I mean, we can literally just copy down the definition first. Just use just literally copy the definition down. This is f evaluated at x plus delta x. Sorry, my delta is a bit weird. Delta x and y minus f of xy. All divided by delta x. This change in value relative to delta x, and taking the limit of that as delta x approaches 0. Of course, we know what f is. We're dealing with a particular f here. So this is x plus delta x, all of it squared, multiplied by y, minus xy. Sorry, x squared y. F of xy is x squared y. F of x plus delta xy is x plus delta x squared y. The rule for f is square the first argument multiplied by the second argument. And that's all divided by delta x. Okay, we have to evaluate that limit. It's not immediately obvious what the limit is, because the numerator is complicated. There's three quantities floating around, an x and a y and a delta x. It's hard to see what's going on, but we have to square this quantity here. So we could expand that a bit, see what's going on. I mean, evaluating limits can be hard, so you want to simplify as much as possible the thing you're taking the limit of. So we square this bracket here, and you'll see you've got an x squared plus a 2x delta x plus a delta x, all of it squared. And that is all multiplied by y, and then your minus delta minus x squared y. Remember, delta x is a two-letter name. for a single quantity. Don't go squaring the delta and squaring the x. It's just delta x all squared. So you might have the name Joe, J-O, something. This is just a two-letter name for a single quantity. Okay, well, this helps us because now we start to see some interaction here. We've got a minus x squared y here and a plus x squared y. Those, of course, are going to cancel. And that has the advantage of eliminating the y's from the situation. So we have 2x, or not, sorry, not quite eliminating the y's. We've got 2x delta xy plus delta x squared y, that's all we have, and divided by delta x. Okay, this is good. The thing is simpler. Can we do the limit? Well, of course, the limit here is complicated because we're taking the limit as delta x approaches 0, but this looks worrying because you've got the quantity delta x in the denominator, okay? Of course, as things get small, if they're in the denominator position, they will be making the whole thing rather large, okay? If delta x is getting very close to 0, because you're dividing by it, it's giving you an ever greater answer, or potentially an ever greater answer. But we don't have to do anything too involved because we notice when you look, there's plenty of delta x is above the line too. So we can actually perform a division to get rid of this delta x in the denominator and cancel it with the delta x's in the numerator. So we get 2xy plus delta xy. Just. Yeah. Now there's no conceptual problem with taking the limit as delta x approaches 0. You've got a quantity here, 2xy, which does not have a delta x in it. So it's unaffected by the limiting process. It just has the value 2xy. Then you've got a quantity here, delta x and y. You're taking the limit as delta x approaches to 0. Well, it doesn't matter what value y has. Whatever value it has, it's multiplied by something which is converging to 0. So the limit of the second term is just going to be 0. So we got a limit of a constant plus a term. The term is approaching 0. So the value to the limit is just whatever that first constant is. Okay, and this gives us the result 2xy. So 2xy is the partial derivative of that function f with respect to x. Okay, that's how we would read it out in English. So. Okay, that more or less brings us to the end. So when I see you in a few hours, I'll be seeing you again at 5. I'll hand them out to you now. We're going to do, we just introduce a little bit more terminology and so on, but then we're going to do an extended example session. Working with a number of examples on this sheet. It's going to disappear before you get this.
3-hour break. There's lessons, 3-hour break, lessons go.
Okay.
Sorry about that.
Yeah, that's fine. Yes, yeah, you need to come and get a booklet. Are you free now?
Yeah, I'm free now.
Yeah, if you just pop upstairs to 115. I'll just be back there in a second. I just have to gather all this stuff, and I'll give you one there. Okay? It's okay. Easily done. First day. Is it? Zhangzhou, is it? Yeah. Yes. JX. 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 Good. Okay.
I think you know my sister, yeah. Boy.
Oi, my. Yes. Yeah. She was I supervised her project a couple of years ago. Yeah. It's good. So she did the MMAT last year, didn't she?
Yeah, I think
she stayed on for the MMAT. Oh wow, you're her brother. You're her little brother. So she giving you loads of advice then for. How is she now? What's she up to? She teacher training, is it?
Yeah, PhD at University of Manchester.
University of Manchester. Right. Good. Excellent. You tell her I said hello.
You are?
Tell her I said hello.
Yeah.
Good. She got fairly high marks, I seem to remember. You know, she's
I did.
tough act to follow.
I know that she got a first on, and that's all I know.
Okay. Yeah. Right. Let me gather my stuff.
Sure.